Let's design Twitter together. Really quickly before we jump in, if you want to try this very question along with dozens of others for yourself, head over to hellointerview.com. There you'll be able to answer questions directly on an interactive AI-powered whiteboard. You'll get instant feedback on your design from an AI trained by myself and my co-founder, a former FANG hiring manager. There's no faster way to ramp up for your upcoming system design interviews, so I highly recommend you go over there and give it a try. Designing a microblogging service like Twitter consistently ranks as one of the top 5 system design interview questions asked at the world's biggest companies like Facebook, Amazon, Netflix, and Google. As a former staff engineer at Meta, I conducted hundreds of interviews, and over that period of time, I saw exactly what it takes for candidates to stand out. As we go, I'll call out those subtle do's and don'ts. My goal is to make you feel as prepared as possible come interview day. Let's stop wasting time and let's jump right in. In any system design interview that you do, the very first step is going to be to make sure that you understand the requirements of the system. Now, there's 2 main goals in this section. First, it's to make sure that you and your interviewer are on the same page before you start designing. Second, it's for you to get a clear understanding of the features that you're going to support in your design. You're going to come back and reference this list time and time again throughout the remainder of the interview. Now, we break the requirements into 2 categories. The first is what we call functional requirements. The functional requirements are the core features that the users expect from the system. So, for example, this would be being able to create tweets. Next, we have the non-functional requirements. These are the system's quality attributes. So security, reliability, performance, that all fits into the non-functional requirements. So for our service like Twitter, the functional requirements would be things like this. The user should be able to create an account and log in. Users should be able to create, edit, and delete tweets. They should be able to follow other users. They should be able to view the tweets of the people that they're following on their homepage. In other words, the timeline. They should be able to like and reply and retweet to other people's tweets. And users should be able to search for tweets. For the non-functional requirements, this system should be able to scale to support hundreds of millions of daily active users. As such, the system should handle a high volume of tweets created and read every day. It should be highly available, ensuring that the system can be accessed at any time of day with 99.999% uptime. The system should ensure the security and privacy of user data, and importantly, it should have incredibly low latency. So there shouldn't be a lot of time that users are spent waiting for the tweets to load. Keep in mind that for the functional requirements in particular, this is far from a complete list. The real Twitter has DMs, complex integrity systems, ad networks, the list goes on and on and on. But the reality is they had 17 years to build it, and we have 45 minutes in an interview. So in your interview, you want to make sure that you pick the core requirements, and then you touch base with your interviewer to make sure that you guys agree on the features that you're going to include in your system. Important pro tip here, do not spend more than 5 minutes on this section. Spending too much time here is one of the largest mistakes that I'll see candidates make time and time again. The reality is that while the requirements are incredibly important, they are not the most interesting part of the interviewer. So get your requirements down and move on to the far more interesting bits. All right, let's start designing this thing. So it's always most logical to work left to right across the request lifecycle when you're designing on a whiteboard. So the very first thing that we're going to add is our clients. We're going to include both a web app or website and a mobile application, iOS and Android. From here, requests sent from the client hit our load balancer. What's a load balancer? Load balancers distribute incoming traffic across multiple servers, and they're key to scalability in just about every single system design interview that you're going to do. Now, when we talk about load balancers, there are 2 relevant points of discussion that are worth bringing up in your interview. The first is the routing algorithm. This determines how the load balancer distributes incoming requests to the backend servers. Common algorithms include round robin, which rotates requests evenly across all servers, least connections, which sends requests to the server that has the fewest current connections, and IP hash, which routes based on the IP address of the client. This ensures that the same IP gets the same server for each request. Second is the layer in the OSI model that the load balancer operates at. So load balancers can operate at different layers. The most common are layer 4, or transport layer. This is like TCP, and layer 7, the application layer, like HTTP and HTTPS. Layer 7 load balancers are interesting because they can make routing decisions based on the actual content of the request, such as the URL or the header. Okay, so for our Twitter-like system, For our routing algorithm, we're going to opt for round robin routing. It's simple, it's fair, we have no need for persistent connections, and our backend servers are going to be stateless, so this works great. And then our load balancer is going to be a layer 7 load balancer. This means that it operates at the application layer and that we can make content-based routing decisions for feature rollouts and then support more complex traffic management and things like this as our system scales. All right, but what are our load balancers distributing traffic to? Well, that's going to be a fleet of servers serving as our API gateway. We're using an API gateway here because we've opted for a microservice architecture. This just means that our service is broken down into smaller independent services that can communicate with one another. And each one of these services is strictly responsible for a specific piece of functionality within the larger system. Now, the API gateway's responsibility is to take the incoming requests from the load balancer and forward them on to the appropriate service. It's worth mentioning that these three components, the client, the load balancer, and the API gateway, are going to be present in roughly 90% of the system design interviews that you do. So when in doubt, this is usually a pretty good place to start. The next thing for us to do is to lay out the key services. Typically, this matches really closely with the system's core functional requirements that we came up with earlier. So let me get those back up on the screen and we'll walk through them one by one. So first, users should be able to create, edit, and delete tweets. Great, that's easy. Let's add a tweet CRUD service to handle exactly that. CRUD just stands for create, read, update, and delete. Now, users should be able to like, retweet, and reply to tweets. Likes and retweets are just updates to existing tweets, so those will be handled within our tweet CRUD service. But for replies, let's create a separate service to handle those. This allows us to scale replies independently, which will be particularly crucial for things like viral tweets. And then let's add a search service to handle searching for tweets. We'll add a timeline service to handle timeline creation. And then lastly, a profile service to handle account creation, profile management. This will also be responsible for managing followers and the social graph. The next step is for us to go service by service, and we're going to ensure that each one is equipped to fulfill their necessary requirements. So let's start with our tweet CRUD service. Again, this needs to be able to create, edit, and delete tweets. It also needs to support tweet likes, retweets. It needs to handle the metadata associated with each tweet. This is things like timestamps, user IDs, and any media attachment. And then in terms of the non-functional requirements, this service needs to be designed to handle really high throughput. This is because tweets, likes, and retweets are some of the most frequent operations on Twitter, particularly reads. So let's make sure that we keep that in mind while designing as well. Let's talk about how we're going to store the tweets. Twitter actually uses an internal NoSQL database that they've named Manhattan. And similarly, we'll use a NoSQL document DB as well, but we're just going to use an open source alternative like MongoDB. This is a solid choice because of MongoDB's performance efficiencies. It's really good for applications that require rapid and frequent read and write operations, just like our Twitter app. It's also a good choice because we won't have any complex joins on tweets. When a user requests a tweet, we just need to return that document. The tweet document itself is just JSON. It's key value pairs that store all the important information about that tweet. Here's an example of what a tweet document might look like. It has who created the tweet, the content of the tweet, metadata like timestamps, hashtags, and mentions, even the location. And of course, we'll include the media, retweets, likes, things like that, all directly on the document. While we've stored references to the attached media directly in the tweet document, we need to store the media itself somewhere. For this, we're going to use an object store like Amazon S3. Now, there's a good reason why media is almost universally stored in blob storage systems like S3. They're built to handle this vast amount of unstructured data, and they ensure that the media retrieval is super fast and seamless no matter what the scale is. So if you're in an interview and you're dealing with media, there's a really high chance that you should be storing it in blob storage, and Amazon S3 is a great choice. Great, so our write path is starting to become super clear. Users are going to send a write post request. Our load balancer will then take that request and send it to our API gateway. Our API gateway is going to forward it along to our tweet CRUD service. And then the tweet CRUD service will upload any media to S3 and create a new document in our document store with the content of that tweet. Updates or edits are going to follow a very similar path. There's one more thing to consider here. We want to make sure that users can't flood our system with write requests. This would usually just be bot activity and would degrade the quality of the service that we're trying to provide. So let's make sure that doesn't happen and add a rate limiter along the write path to limit the number of tweets that any given user can create over a period of time. After that, we'll just add our arrows and our write path is looking good. Now let's move over and focus on our read path. Our main concern here is that things are going to be lightning quick. So to ensure that, let's make sure that we add a cache on the read path, which is going to cache our popular tweets. This cache, which can be either Redis or Memcache, is going to ensure that the frequently accessed tweets are served rapidly, and they don't need to hit our database every single time. Last thing here, in order to further optimize content delivery, especially for our global users, let's also add a CDN to distribute and serve the static content, media assets, and even frequently accessed tweets. This is going to put that content closer to the user's geographic location. This will reduce latency and ensure that people all around the world have a snappy user experience while browsing our site. We're just going to add our last handful of arrows here, and just like that, the read path looks great. All right, let's keep working our way down our list of services, moving on now to our reply CRUD service. For writes, we're going to store replies in a separate document store. Now, I know what you might be thinking, and that's why don't we just store replies directly within the tweet document? And to be honest, this isn't a terrible idea, particularly if we had a really small service. But there's a list of compelling reasons for why we want to keep them separate. The first is scalability. Popular tweets can garner thousands of replies. So storing them separately not only ensures that the tweet document doesn't become too large and unwieldy, but more importantly, it allows us to scale the replies service entirely independently. Now, the second reason is for performance. By keeping replies separate, we can fetch a tweet without necessarily loading all of its replies. This makes the read really fast for a tweet. And if you've ever used Twitter, you see exactly this. You load a tweet and you see maybe the first dozen, 20, 50 replies, but it's not until you scroll lower that you load the remainder of the replies. And then just like with replies, we're going to add a rate limiter on the write path to limit the negative impact that bots can have on the service. Then we'll just add our arrows, and just like that, the write path for our replies looks good. Now, when it comes to reading these replies, we're going to mix things up just a little bit. Because instead of letting users read replies separately, which if you think about it doesn't make that much sense, we're going to be bundling them right in with the tweets. So this means that when you pull up a tweet, you'll automatically see its replies, or at least a portion of them. To make this snappy, our reply database needs to be indexed by tweet ID. So this means every time we go to grab a tweet, we're also swiftly fetching and caching its replies from the replies DB. Here's an example of what a reply document might look like. As you can see, it looks really similar to the tweet document. The notable addition being that tweet ID field, which we built the index on. Awesome. Taking a step back, we can now create, edit, retweet, like, and reply to tweets. Our Twitter app is starting to shape up really nicely, and at this point, we have a pretty usable product. So continuing to move down our list of services, the next thing we get to is search. Twitter search, like many of these components, is really complex and could be an interview question all on its own. That said, we'll take a simplified approach and just handle the basics here. We're going to need searches to be lightning fast. So while the simplest approach here would be just to iterate through our tweets in our document DB to try to find tweets that match any search terms, we're instead going to add a separate text-based index with Elasticsearch. We'll create reverse indexes on tweet content, username, and hashtag within Elasticsearch, which is going to allow us to quickly search for specific tweets, profiles, or trending topics with minimal latency. Elasticsearch is a distributed search engine that's designed to handle really large datasets with low latency and high reliability. So it's particularly useful for applications that require full text search like our Twitter app. If you're in an interview and you need full text search, Elasticsearch is likely a really strong bet. Data is going to make its way into Elasticsearch via what is called change data capture, or CDC. This process captures and tracks changes in the tweet data, ensuring that our Elasticsearch index remains up to date with the latest information from our tweet document store. So as updates are made to the TweetDB, those changes will automatically be propagated to Elasticsearch. Next up is the timeline service, and this is where things tend to get really fun. And in an interview that's about a social media site, whether it's Design Facebook or Design Twitter, you're often going to spend a good amount of the interview on this exact service. Now, for our purposes, we're going to simplify things a bit, and we're going to generate a timeline that's just made up of posts from your friends. This means that we don't have to focus on a recommendation system at all. The simplest way to construct a timeline is by doing what's often referred to as fanout on read. When a user requests their timeline, we query the list of accounts that they follow, fetch all of the tweets from these accounts, sort by time, and then return the timeline. As you can tell, this is pretty slow and expensive, so it would fail to satisfy our non-functional requirements around low latency retrievals. So instead, we can leverage the power of asynchronous operations by updating friends' timelines whenever a user creates a new tweet. This strategy is termed fanout on write. Here's how it works. For every newly created tweet, they're going to get promptly placed on a message queue. This queue acts as a buffer. It ensures that we're not immediately overwhelming subsequent operations, especially since so many tweets are often created at the exact same time. Now, workers dedicated to our fanout service are always on the lookout. They're going to be pulling these tweets off of this message queue, one after another. For each tweet that they grab, they'll run a query to fetch the list of followers for that tweet's author. Once we have the list of followers, then the magic happens. Each follower has a timeline cache, a quick access store that holds the most recent tweets from the people that they follow. Our worker's job is to update this cache. It takes the new tweet and prepends it to the start of each follower's timeline cache. This makes sure that the next time any of these followers check their timeline, the new tweet is right there at the top waiting for them. So this fanout on write approach, while it's more write intensive, ensures that reading our users' timelines is lightning fast because the data is already prepared and just waiting in that cache. It's a trade-off that prioritizes read speed, which matches our non-functional requirements from earlier, so it's great. There is one catch though, and that's for users with millions of followers like Elon or Drake. The sheer volume of updates that we would need to make to all of their followers' caches could overwhelm the system. So for these, call them mega influencers, we need a hybrid approach. While fanout on write works well for the average user, for these high-profile accounts, we might want to lean towards fanout on read. This means that instead of immediately updating every follower's timeline when a celebrity tweets, we wait. When a follower of Elon or Drake checks their timeline, the system then fetches the latest tweets from the mega account and integrates them into the user's feed from the cache. All right, we're almost there. All we have left is the profile service. As a quick reminder, this needs to support creating and managing both user profiles and followers. We'll offer a simple SQL database for the user data. This will be traditional relational rows with columns for things like username, email, bio, and all that good stuff. SQL is a good choice for Twitter's user data because it allows for efficient querying on structured user attributes. It ensures data integrity with ACID transactions, and it can handle complex joins and aggregations for user analytics. For the follower connections, we're diving into a graph DB. Why? Well, graph databases are tailor-made for mapping out networks, especially social ties. Plus, as our app grows, this graph becomes a goldmine for advanced features like recommendation systems, suggesting new followers, and keeping things safe with our integrity system. We're also going to spin up a separate service for auth, which our profile service will lean on for authentication and authorization. Why separate this out? Well, authentication and access management are critical and specialized tasks. By isolating them, we ensure tighter security, more focused maintenance, and most importantly, the flexibility to integrate with other services or third-party systems in the future without tangling up our main user profile logic. Oops, it looks like we missed one edge from our CDN to our client. So let me go back and add that. And then boom, there it is. A complete system designed for a service like Twitter. But we can't celebrate just yet. No system design interview is complete without touching on security, monitoring, and testing. So let's spend a moment for each of those. Let's start by briefly touching on security. There are four main considerations here. The first is authentication and authorization. This is to make sure that every request comes from a legitimate user and that the users have the right permissions to perform the requested action. In our system, this is all handled by our auth service under the profile service. Second is data encryption. All user data, both at rest and in transit, should be encrypted. We use HTTPS for encrypting data that's in transit, ensuring that the data exchange between our client and the servers remains confidential and tamper-proof. For data at rest, most modern databases have native support for data encryption, so this is usually as simple as just flipping a switch. Next is rate limiting. Now remember, we already discussed rate limiting for tweets and replies specifically, but it's also crucial to prevent DDoS attacks. For this, we do IP rate limiting within our API gateway. This means that requests from a single IP address are limited to a certain number within a specified time frame, preventing any single user or bot from overwhelming our system. Lastly, we need to consider input validation on our client. Here, we'll validate and sanitize any user input to prevent things like SQL injection, cross-site scripting, or other malicious attacks. Typically, we'll want to protect against things like this, both on the client and on the server. Now let's delve into monitoring. there are three key aspects to consider. The first is system health checks. It's crucial to keep an eye on the health of our service. If any component, like our tweet crud service or our profile service, goes down or becomes unresponsive, we need to know this immediately. For this, we can utilize tools like Prometheus and integrate with Grafana so that we have a nice visual dashboard. These tools will monitor our services and provide real-time metrics on their performance. Second is logging. Every action, from a tweet being posted to a user logging in, should be logged. This aids in debugging and tracking potential security threats. In our design, we use an ELK stack, which stands for Elasticsearch, Logstash, and Kibana. Elasticsearch will store our logs, Logstash will process them, and Kibana will provide a visual interface to analyze these logs. All our services, including the API gateway and the databases, will send logs to this central system. To avoid having to draw out all those lines, I'm going to simply add a general ELK component to our design, and we're going to have to use our imagination to understand that all of the services have an edge to this component. Last up is real-time alerts. If there's a sudden surge in traffic or multiple failed login attempts, we need to be notified. Integrating something like Alert Manager or PagerDuty with Prometheus that we talked about earlier can help send notifications via email, Slack, or any other channel so that we're immediately notified and can quickly respond when something bad happens. Last but not least, let's briefly talk about testing. First up is load testing. Before introducing any new feature, we need to see how our system, especially services like the tweet service or profile service, hold up under the new pressure. This will allow us to pinpoint bottlenecks and potential failures. Second is automated testing. Given our microservice architecture, it's particularly important that our services integrate seamlessly. Every time there's a code change, our CI tools or our continuous integration tools, such as Jenkins or maybe GitHub Actions, are going to automatically run both unit tests, which check individual components, and integration tests, which ensure that the services communicate effectively. Lastly, we need to talk about testing our backup and recovery. So our data is invaluable. Regular backups are non-negotiable, and we'll need to periodically test our recovery process. This is to ensure that in the unlikely event of a system failure, we can restore our Twitter clone's operation swiftly. We just walked through the design of a simplified Twitter. We talked about microservices, scaling, we talked about handling timeline generation, data storage, and all of the many intricacies that come along with it. We touched a little bit on security and monitoring and testing, and at the end of the day, I think we put together a pretty robust system that would do excellent in a system design interview. Now, if you want to try this interview for yourself, and I strongly recommend that you do, then you should head over to hellointerview.com. And this is where you can try this interview or dozens of others on an AI-powered interactive whiteboard where you'll get instant feedback from an AI that was trained by myself and my co-founder who's a former FANG hiring manager. All right, thanks so much for watching, everybody. If you have questions, leave them in the comments. I'll be answering them as quickly as I can.